Good morning, students. Today we see about the 11th standard 7th unit. 11th standard 7th unit, the continuation of this lesson, capillarity. Okay, today we see about the topic capillarity. In previous class we see about the angle of contact. What is angle of contact and what is the excess of pressure inside a liquid drop, a soap bubble and an air bubble. First of all, what is meant by angle of contact? The angle that between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid. It make one angle that is called as the angle of contact between the solid and liquid. Okay, that angle is denoted as theta. Okay, that angle is denoted as theta. Then it consists of here consider the three interfaces. What are they? Liquid air, solid air and solid liquid. Okay, so the point of contact is denoted as O. So the liquid air is denoted as TLA and the solid air is denoted as TSA and the solid liquid is denoted as TSL. Okay, next we see about the excess of pressure inside a liquid drop, a soap bubble and an air bubble. Okay, then today we see about the capillarity. Today we see about the capillarity. Okay, today we see about the capillarity. First of all, what is meant by capillarity? Here the word capillo means a hair in Latin. Okay, the word capilla means a hair in Latin. If the tubes were thin hair, okay, if the tubes were hair thin means then the rise would be very large. Okay, if the tube were very thin means the rise would be very large. Here it means that the tube having a very small diameter. Okay, in other words it is called as that the tube consists of one tube. The tube have a very small diameter, that is called as the capillary tube. When a glass capillary tube opens at both ends is dipped vertically in water, the water in the tube will rise above the level of water in the vessel. Okay, in case of mercury, the liquid is depressed in the tube below the level of mercury in the vessel. See the figure 7.29. See the figure 7.29. Here first water is there, okay, then next mercury is there. First of all we dipped one capillary tube inside the water beaker. What happened? That the capillary tube contained the rise level of liquid. When compared to the beaker, the capillary tube contained the highest level of the liquid. Okay, then see the second figure. Here mercury is there. Okay, the beaker also containing the mercury and the capillary tube is also containing the mercury. Here when compared to the beaker, that capillary tube contained the low level of mercury. Okay, so here it is a negative case and water here it is a positive case. Okay, in a liquid whose angle of contact with the solid is less than 90 degree. Already we studied in the previous class. Less than 90 degree means it make the acute angle. Okay, so it suffers the capillary rise. On the other hand, in a liquid whose angle of contact is greater than 90 degree. Okay, so in a liquid whose angle of contact with a solid is less than 90 degree means it make the angle, it make acute angle. Okay, so suffers the capillary rise. On the other hand, in a liquid whose angle of contact is greater than 90 degree means it make the obtuse angle, so it suffers capillary fall. Okay, less than 90 degree means capillary rise is there and greater than 90 degree means the capillary fall is there. Okay, then the rise or fall of a liquid in a narrow tube is called as the capillarity or capillary action. So the rise or fall of a liquid in a narrow tube is called as the capillarity or capillary action. Depending on the diameter of the capillary tube, the liquid rises or falls to the different height. Okay, then see the table 7.4, capillary rise and capillary falls. First here the angle of contact, that is the theta value will be 0 means what is the strength of coercive force and adversive force. If the theta value will be 0 means the coercive force is weak but the adversive force is strong. Then the degree of wetting. Degree of wetting will be perfect wetting, and the meniscus will be plain meniscus. What is meant by meniscus? That's shape of the liquid, that is called as here plain. Okay, so the rise or fall of the liquid in the capillary tube is neither rises nor depressed. Okay, neither rises nor is depressed. Okay, suppose the angle of contact, the theta value will be less than 90 degree. Less than 90 degree means here the coercive force is weak, adhesive force is strong, which is similar to that of the angle theta 0. Okay, so here the degree of wetting is high. Okay, degree of wetting is high. The meniscus is, it make the concave surface. Okay, it make the concave surface. Here the rise or fall of the liquid in the capillary tube is rise of the liquid, because it make the concave, so that rise of the liquid. Okay, the next, the theta value will be less than 90 degree. Greater than 90 degree means it make the angle obtuse. So here the coercive force is strong, but the adhesive force is weak. Then what is the degree of wetting? Here the degree of wetting is low. Then meniscus, it make the convex shape, then fall of the liquid. Okay, so this is the capillary rise and capillary fall. Okay, suppose here capillarity means the diameter of the tube, that is called as the capillary. Okay, so here consider the two cases. In one case we take the beaker and pour some water. Another case you take the beaker and pour the mercury. Okay, now you place the two capillary tube on the two beakers. What happened? The water in the beaker that containing water, the capillary tube contain the rises of water level. Okay, but the beaker that contain the mercury, here when compared to the beaker in mercury, the capillary tube have the lower level of mercury. Okay, so this is called as the capillary rise or capillary fall. Okay, next we see about the practical application of capillarity. Before that, you see the figure 7.30. Okay, before that we see the figure 7.30. Here they consider the three cases. First one, water on silver surface. Water on silver surface. Then second diagram, B diagram, glass plate on water. Then third diagram, glass on mercury. Okay, then next we see about the practical application of capillarities. First, due to capillary action, the oil rises in the cotton within an earthen lamp. Likewise, the sap rises from the root of a plant to its level and branches. Then next, the absorption of ink by a blotting paper. Already I said this example, isn't it? If we take one paper and you pour the ink. Okay, what happened? That paper will absorb the ink. Okay, so this is the capillarity action. Okay, then the capillary action is also essential for the tear fluid from the eye to drain constantly. Then cotton dresses are preferred in summer because the cotton dresser have fine pores which act as the capillary for the sweat. Okay, so these are the practical applications of capillarity. What are they? Oil rises in the cotton, then absorption of ink by a blotting paper, then eye to drain the tears constantly, then cotton dresses. Okay, because it has some fine pores which act as the capillaries for sweat in summer. Okay, next we see about the tension by capillary rise method. Surface tension by capillary rise method. Okay, so here the pressure difference across a curved liquid air interface is the basic factor behind the rising up of water in narrow tube. Okay, so because here it influences the gravity is ignored, so the capillarity rise is more dominant in the case of very fine tube, but this phenomena is outcome of the force of surface tension in order to arrive a relation between the capillary rise height. Okay, see, and a surface tension T. Consider a capillary tube which is held vertically in a beaker that containing the water. The water rises in the capillary tube to a height due to the surface tension. See the figure 7.31. Here consider that beaker. Okay, that beaker contains some water and one capillary tube is inserted into that beaker. What happened? There will be a rise of water in the capillary tube. the capillary there is some tension is involved, that is taken as capital T, and it that capillary tube height is denoted as h. Okay, the surface tension force Ft. Ft means the force due to the tension. Okay, so the Ft act along the tangent. Okay, this Ft act along the tangent. If some force that act along the tangent means here at the point of contact downward and the reaction force upward. So the surface tension T is resolved into two components. Okay, if some force that act along the tangent means here the two forces are there, one is downward and upward. That means here the surface tension is resolved into the two component. One is the horizontal component and another one is the vertical component. Here the horizontal component is taken as the T sin theta and the vertical component is denoted as the T cos theta. Here acting upward all along the whole circumference. Okay, so only the vertical component only involved in this equation. So the total, if we want to find the total upward force. Okay, we want to find the total upward force. So the total upward force, which is equal to, here the total upward force contains some vertical component. What is the value for vertical component? T cos theta. Okay, so here we apply T cos theta into 2 pi r. So the total value will be 2 pi r T cos theta. Here the theta is the angle of contact and r is the radius of the tube, and here some density. Okay, here some what is the density? Density is denoted by the letter rho. Okay, so here the water is there, so we want to find the density of water, so we put rho. Okay, rho be the density of water and h be the height to which the liquid rises inside the tube. Okay, so these are the total upward force. Okay, next we have to find the volume of liquid column in the tube V. Okay, next we have to find the volume of liquid column in the tube V. So what is the formula for that? Means volume of the liquid column in the tube V, which is equal to volume of the liquid column of radius r, it having some height h, plus volume of the liquid of radius r and it having the height r. Okay, don't confuse here. In first one, volume of the liquid column of radius r, height h. Okay, in the second one, volume of the liquid of radius r and height also r, minus volume of the hemisphere of radius. Okay, minus volume of the hemisphere of radius. Next we have to apply the value for this volume. Okay, first we want to find the volume of liquid column in the tube. Okay, that is taken as capital V. Okay, that is taken as capital V. Then what is the formula for volume of the liquid column of radius r, height h, means that is the volume of the cylinder, that is taken as pi r squared h. Pi r squared h plus here also volume of the liquid of radius r, here also the volume for cylinder. So but here what is the value for height? R. Okay, so that instead of h here we put pi r squared into r. Have you all understand? Pi r squared into r, then minus, here minus is there in this formula, so minus what is the volume of hemisphere? 2 by 3 pi r cube. Okay, what is the value for hemisphere? Volume of hemisphere 2 by 3 pi r cube. Have you all understand? First we have to find the volume of liquid column, that is denoted as capital V, which is equal to, then here volume of cylinder. Okay, volume of cylinder formula is pi r squared h. Okay, here radius r and height h. Okay, so which is V is equal to pi r squared h, plus next also volume of liquid of radius r and height r. Okay, here also we have to apply the volume of the cylinder, but here that having the value for height is r, so instead of pi r squared h, pi r squared, instead of this h we have to put r. Okay, so pi r squared into r minus, then what is the value for volume of hemisphere? 2 by 3 pi r cube. Okay, so 2 by 3 pi r cube. Okay, next we have to find V, which is equal to, we have to apply all these values, isn't it? Yes, next V, which is equal to pi r squared h, then plus, I take this plus 2 inside. Okay, so plus pi r squared height, sorry, r cube, okay, not height, r cube. Okay, why r cube? Here pi r squared into r is there. Okay, so pi r cube minus 2 by 3 pi r cube. Okay, here I write the same here, pi r squared height. Okay, here also pi r cube is there, here also pi r cube is there. Okay, so I take the LCM for this. Okay, here minus 2 by 3 is there, here only 1 is there. Okay, so I take the LCM for this. LCM means I have to multiply this 3 into this side. Okay, so 3 into pi r cube, 3 pi r cube minus 2 pi r cube upon the whole upon 3. Okay, whole upon 3. Have you all understand? Then next, here the same one, pi r squared height plus, here 3 pi r cube is there, here minus 2 pi r cube is there, here pi r cube same, so then we have to subtract 3 minus 2, 1, so 1 by 3 pi r cube. Have you all understand? So finally we get the value v is equal to pi r squared height plus 1 by 3 pi r cube. Here pi r squared height plus 1 by 3 pi r cube. Have you all understand? Okay, next. Okay, next here the upward force that support the weight of the liquid column above the free surface, therefore 2 pi RT. Okay, the upward force that support the weight of the liquid column above the free surface, therefore what is the value for V? That is, the V is the upward force. So what is the value for V? 2 pi RT cos theta, isn't it? Yes, 2 pi RT cos theta, which is equal to pi r squared h plus h into h plus 1 by 3. Okay, why here I take the pi r squared common. Okay, here I take the pi r squared common. So if I take the from this equation v is equal to pi r squared h plus 1 by 3 pi r cube, I take the pi r squared common. Okay, so pi r squared common means what is the remaining thing here? H is there, h plus 1 by 3. Here already I take 1 r squared, pi already I take outside, then r squared already I take outside, then what is the remaining? R. Okay, so h plus 1 by 3 r into rho g. Why here we put rho g? Rho means here some water is there, so we have to find the density of water. So here rho is denoted as the density of water, and g, here some gravitational force is involved. Okay, so the 2 pi RT cos theta, which is equal to pi r squared h plus 1 by 3 r rho g. Okay, from this equation we have to find the T value, that is the tension value. So T, which is equal to, wait, T which is equal to, I take, what is the, here what are the terms are there? Pi r squared h plus 1 by 3 into r rho into g divided by, we want only the T value. Okay, so we take all the remaining things into denominator term. So what are the remaining things? 2 pi r cos theta. Okay, 2 pi r cos theta. Here we have to cancel this pi cancel, then this r, here one r will be cancelled. Okay, then what is the remaining thing? T, which is equal to, here one r is there, so r h plus 1 by 3 into 1 by 3 r into rho g upon 2 cos theta. Okay, have you all understand? So this is the tension value. Okay, T, which is equal to r into h plus 1 by 3 r into rho g upon 2 cos theta. This is the surface tension value. Okay, next, if the capillary is a very fine tube of radius, that is the radius is very small, means then r by 3 can be neglected. Okay, if the capillarity, that is the radius value will be very small, means the r by 3 value will be neglected. Therefore what is the T value? If r by 3 is neglected means if r by 3 can be neglected means then what is the remaining value? T, which is equal to r, then r into height. Here height is there, r by 3 is neglected, so outside rho g is there upon 2 cos theta. Okay, so what is the remaining thing? R rho g h. Okay, this is r, so r rho g h upon 2 cos theta. Okay, so this is the t value. This is the t value. If the r by 3 value will be neglected, mean what is the tensor value? T is equal to r rho g h cos r rho g h upon 2 cos theta. So this is the t value. Okay, next the liquid rises through a height h. Okay, if suppose the liquid rises through a height h means then what is the height value? If we want to find the height means here the height which is equal to, what is the t value? T is equal to pi r t cos theta. Sorry, t is equal to h plus r rho g h upon 2 cos theta, isn't it? Yes, here height which is equal to, take the reciprocal. Okay, take the reciprocal of this equation 7.33. So 2t cos theta upon r rho g. Okay, if you want to find the height value means we have to take the reciprocal. So 2t h theta 2t cos theta upon r rho g. Okay, then here the height is inversely proportional to the radius of the capillary tube. The height of the capillary tube is inversely proportional to the radius of the tube. Okay, so have you all understand? So this implies that capillarity rise height is inversely proportional to the radius r of the tube. That is, the smaller the radius of the tube, greater will be the capillarity. Smaller the radius of the tube, greater will be the capillarity. Okay, so have you all understand? So what is the surface tension by capillary rise method? First we have to consider one beaker. Okay, and the beaker is filled with water and one capillary tube is inverted into this beaker. Here it acts as a tangent. The surface tension force act along the tangent at the point of contact. So here two forces are involved. One is the downward force and another one is the upward force. Okay, so here the horizontal so it is resolved into two component, means the horizontal component is denoted as the t sin theta and the vertical component is denoted as the t cos theta. Okay, so next we have to find the upward force. Here the upward force is taken as the whole circumference. So the total upward force is equal to vertical component only involved in this equation. So what is the vertical component? T cos theta. So T cos theta, what is the circumference of the circle? 2 pi r. So T cos theta into 2 pi r, which is equal to 2 pi r T cos theta. Here the theta is the angle of contact and r is the radius of the tube. Here some density of water is also involved. What is the letter denoted for the density? Rho. Okay, so rho is the density of water and h be the height to which the liquid rises. Okay, so then next we have to find the volume of the liquid column, capital V. So the volume of the liquid column, capital V, which is equal to volume of the liquid column of radius r and height h plus volume of the same one, that minus, but it having the height r instead of h. Here we have to put r minus volume of the hemisphere of the radius r. Okay, then next we have to apply the value of this volume. So V, which is equal to, what is the volume of the cylinder? Pi r square h. Okay, here the height is height, so that we put pi r squared h. Next also the volume of the cylinder only, but here the height value is r. Okay, so instead of pi r squared into h, instead of this h we have to put r. So here pi r squared into r minus, then what is the volume of the hemisphere? 2 by 3 pi r cube. So 2 by 3 pi r cube. From this we have to find the V value. So V equal to pi r squared h plus 1 by 3 pi r cube. Okay, here the upward force only support the weight of the liquid column. So the free surface, therefore 2 pi, what is the value for V? That is the upward force value. So 2 pi RT cos theta, which is equal to this value. Here it includes the rho G. Rho means the density of water and G is the gravitation. Okay. So next we have to find the T value. So T, which is equal to pi r square. I take this 2 pi r cos theta into the downward. So here 2 pi r cos theta. Okay. Then pi cancelled and 1 r will be cancelled, and finally we get the numerator term r into h plus 1 by 3 r rho G upon, then the denominator term is 2 cos theta. If the capillary is a very fine tube of radius, here the radius will be very small, so the value r by 3 can be neglected. Then finally we get the T value, which is equal to r rho G h upon 2 cos theta. Okay. Now the liquid rises through a height. H means we have to find the height value, means I take this height to this side. Height to this side means this equation 7.33 equation will be changes into reciprocal. Okay. So the numerator term comes to the denominator term and the denominator term comes to the numerator term. So H, which is equal to 2t cos theta upon r rho G. Okay. Here have you all understand? Here the height is inversely proportional to the radius. The height of the capillary tube is inversely proportional to the radius of the capillary tube. Okay, so this is the surface tension by the capillary rise method. Okay, next we have to see about the topic of applications of surface tension. What are the applications of surface tension? Here the first one is mosquito lay their eggs on the surface of water, because to reduce the surface tension of water a small amount of oil is poured. This breaks the elastic film of water surface and eggs are killed by drowning. இது நம்ம நிறையவே பார்த்துருப்போம். இப்போ ஒரு சர்ஃபேஸ் ஆஃப் வாட்டரில் வந்து வாட்டர் சர்ஃபேஸில் வந்து இந்த கொசு வந்து எக் லே பண்ணி வச்சதுன்னா அந்த சர்ஃபேஸோட டென்ஷன் வந்து ரெடியூஸ் பண்ணணும்னா வாட்டரோட சர்ஃபேஸ் டென்ஷன், இஃப் யூ வாண்ட் டு ரெடியூஸ் த சர்ஃபேஸ் டென்ஷன் ஆஃப் வாட்டர் மீன்ஸ் we have to pour some oil onto that water. Okay, then what happen? This that oil break the elastic film of water surface, then the eggs are killed. Okay, then next one, chemical engineer must finely adjust the surface tension of the liquid so it forms the droplets of designed size, and so it adheres to the surface without smearing. So this is used in the desktop printing to paint the automobiles. This technique was used in the automobile painting and decorative items. Okay, the next one, the specks of dirt get removed when detergents are added to the hot water while washing cloth, because the surface tension is reduced. Okay, then the last application is a fabric can be made waterproof by adding some suitable waterproof material, that is wax, to the fabric. This increases the angle of contact. So these are the applications of surface tension. Okay, then take the next page, take page number 82. Next topic is Bernoulli's theorem. I just give the introduction to this Bernoulli's theorem. The first one is equation of continuity. Okay, the first one is equation of continuity. So in this equation of continuity, in order to discuss the mass flow rate through a pipe, it is necessary to assume the flow of fluid is steady. The flow of fluid is said to be steady if at any given point the velocity of each passing fluid particle remain constant with respect to time. Under this condition, the path taken by the fluid particle is a streamline. Okay, consider one tube. Inside the tube, the liquid will be flowed through this tube. That flow of liquid will be steady. That means the flow of particle is a streamlined. Okay, so consider a pipe. That pipe having the length AB. Okay, it consists of some varying cross section. What is mean by cross section? Here the cross section is this is the cross section. Okay, here also one cross section is there. So these are the cross sectional area. Okay, so consider a pipe AB. It consists of varying cross-sectional area A1 and A2, such that here A1 greater than A2, a non-viscous, and what is meant by non-viscous and incompressible fluid. it does not adhere to each other. Okay, so that is called as the non-viscous and incompressible fluid. Okay, பிசுபிசுப்பு தன்மை இல்லாத liquid. Okay, so it is called as the non-viscous and incompressible liquid that flows steadily through a pipe with having some velocities also. V1 and V2 are the velocities in the area of cross-sectional area A1 and A2 respectively. Okay, then see the figure 7.32. This is the streamline flow of fluid through a pipe having the varying cross-sectional area A1 and A2 having some velocity V1 and V2. Okay, then next we have to find let here the M1 be the mass of the fluid flowing through the cross-sectional area A. Okay, M1 be the mass of the fluid flowing through the cross-sectional area A through the section A in time t. Okay, that means starting first அதுக்குள்ள நுழைய அந்த ஏங்கிற ரீஜியனுக்குள்ள என்டர் ஆகக்கூடிய அந்த லிக்யூடோட மாஸ் will be taken as M1 at a time del t. Okay, the time is denoted as del t, so that M1 which is equal to A1 V1 del t rho. Why here we put A1 V1 del t rho? A1 is the cross-sectional area of A and V1 is the velocity of that particular area and temperature is the particular time, and rho is already we know that rho is the density of some water. Okay, then next M2 be the mass of fluid that flowing through the section B in time del t. Okay, now that leaves through the B. Okay, so in that case that mass is taken as M2. Here A2 is the cross sectional area, V2 is the velocity in that particular area, and del t is the time, and rho is the density of water. Okay, now for an incompressible liquid, here the mass is conserved. Mass is conserved means what is the meaning of conserved? M1 which is equal to M2. That means the mass of the liquid 1 which is equal to the mass of the liquid 2. So M1 which is equal to M2. Then we got to apply the values of M1 and M2. Okay, have you all understand? So what is the value for M1 here? A1 V1 del t rho which is equal to, then what is the value for M2? A2 V2 del t rho. Okay, A2 V2 del t rho. Then next we have to apply this value. Then finally here also del t is there, here also del t is there, so cancel. Here also rho is there, here also rho is there. Okay, so the del t and rho will be cancelled. Okay, then next then finally we get the value A1 V1 which is equal to A2 V2 which is equal to AV, that is called as the constant term here, which is called as the this is called as the equation of continuity. This is called as the equation of continuity, and it is a statement of conservation of mass in the flow of liquid. Okay, in general here the value AV will be constant means that the volume flux or the flow rate remains constant. Okay, throughout the pipe. AV constant means the volume of the liquid throughout the pipe will be constant. In other words, smaller the cross section, greater will be the velocity of liquid. If the cross section value will be smaller means the velocity of the fluid will be greater. Okay, so this is called as the equation of continuity. Okay students, have you all understand? So today we see about what is meant by capillarity. What is meant by capillarity? Capillarity is the diameter of the capillary tube, that is called as the capillarity. Okay, next we see what are the practical applications of capillarity, and what is the surface tension by the capillary rise method. Then we have to find the some applications of surface tension. Then finally we see the equation of continuity. What is the formula for equation of continuity? A1 V1 which is equal to A2 V2, that means AB which is equal to constant. Okay, AB constant means if the smaller the cross sectional area will be smaller means the velocity of the liquid throughout the pipe will be greater. Okay, so this is the continuity, equation of continuity. Okay students, tomorrow we see about the Bernoulli's theorem and its application. Okay, so today so this is the time for your homework. Already I give some question, isn't it? What question I give in 6th unit? I asked to study the variation in depth and latitude. Yes, in 6th lesson, page number 19, already I give the variation of altitude and variation of depth and latitude I give yesterday. Okay, today you write and study the variation of G with altitude. That is the page number 19 only. Okay, start from the consider an object up to gravity G decreases up to the page number 19. Okay, so this is the homework and study work for you. Okay, so okay students, thank you. Tomorrow we see the Bernoulli's theorem and its application.